First of all, I'd like to thank Lance for inviting me. This is my second time in Taiwan, and it seems to always rain when I'm on this. It should be okay. I'll talk louder. So today we're going to explore what's called the quantum to classical transition, okay, in mesoscale physics, and using a particular kind of system called optomechanical systems. Okay, so this talk is designed such that you don't have to know anything about these words. I'm going to explain them all to you, and then I'm going to show you a kind of system that explores this regime. So to understand this quantum to classical transition, we have to first ask ourselves a question, and the question is, how does the classical world emerge from the underlying rules of quantum mechanics? Okay, this is what I mean by the quantum to classical transition, and if we think about it for a little bit and we recall what we learned in class, then we somehow intuitively guess that small objects behave quantum mechanically and large objects behave classically. Okay, this is kind of what we're taught. All right, and indeed this is true, right? So we can kind of make ourselves the scale from quantum to classical, and of course we can put everyday objects on this classical side here. So of course the Earth and the orbit of the Earth, that's completely described by Newtonian mechanics. A bicycle, the same thing. Cells in your body, okay, also obey Newtonian physics for the most part. The proteins inside those cells behave a little bit quantum mechanically because we have bonds that behave quantum mechanically. Breaking bonds, pi bonds, things like this require the rules of quantum mechanics. But the overall protein itself can be described classically. And of course, if you go deeper and deeper into the quantum regime, then you have things like atoms, the nuclei, and because I ran into someone who did string theory on the elevator, I just put in a little string theory shape here. Okay. So the basic idea is, as the mass gets smaller, I don't think this has mass, but sorry. Okay, as the mass gets smaller, you become more and more quantum mechanical. But the idea is this gradient from yellow to blue always constant? Or can we start to push this yellow part deeper and deeper into this, what we call classical regime? Okay, so can I observe quantum mechanical effects in things that we typically think of as classical objects? Okay. And the answer, at least in principle, is yes. Okay. And there's an entire field of physics devoted to this, and this is what's called nanomechanics. Okay. So nanomechanics, these are devices that people build in the lab. Here are 3 examples of these, where you have essentially a harmonic oscillator, a simple harmonic oscillator with some appreciable mass. Okay, and the goal is to try to tease this mechanical oscillator into some quantum mechanical state. Okay, so these devices here are quite small. This is something like 50 microns. This guy here is about 30 microns. So these guys, at least to date, are quite small, but the goal is to push this field deeper and deeper into the classical regime and keep increasing mass and see how far we can go. Okay. So to understand why objects with large mass behave classically and things like atoms behave quantum mechanically, we have to return to the basic problem that we all have encountered, and this is Schrodinger's cat, right? So Schrodinger's cat is the paradox that he came up with in 1935, where if you put a cat in a box with some poison gas attached to a radioactive decaying atom, and you shut the box, if you wait an appreciable amount of time, then the life or death of the cat is entangled with the quantum mechanical decay of the atom. Okay. And if you wait long enough, or until at least the atom has a 50% chance of decaying, then if you looked at the state of just the cat alone, what you would find is in a superposition, 50-50 of being dead, or 50% of being alive. Okay, and this is the thing we always encounter in quantum mechanics, the basic example of this quantum classic kind of paradox between the two. Okay, but what's not usually discussed is how do you solve this? Right, so how do we actually solve this paradox? Well, first let's see what happens. Right? So we put the cat in the box, right? And we have this 50-50 mixture of dead and alive. And of course, Schrodinger, he can go and open the box. Sometimes the cat's alive, right? And he can just repeat the experiment as many times as he wants. no matter how many times he repeats it, he finds out the cat is either dead or alive. He never sees this superposition state. So in quantum mechanics, there's a word for what Schrodinger is doing, and every time he looks into the box, he's making what's called a measurement. Okay. So that is the term that is used in quantum mechanics. And the question is now, is the cat simultaneously dead and alive before I or Schrodinger measures? Okay. This is the meat of the problem, and of course, the answer is absolutely not. And the reason it's absolutely not is not discussed in quantum mechanics at the undergraduate or graduate levels, but it's because something called the environment is also making measurements on his cat. Okay, so what do I mean by an environment? Well, an environment includes many things. Here I have two examples. So for example, the cat needs to breathe oxygen, otherwise he would be dead. Wouldn't be a very interesting problem. So there's gas molecules inside this box. The gas molecules are moving around quite fast. And of course, they interact with the cat, bouncing off of him. Okay? These interactions between the cat and the gas molecules, okay, this interaction is also a measurement. So the gas particles in the box are always making measurements. In addition, we always have photons. They might not be visible photons, maybe infrared, radio wave, it doesn't matter. These photons are also making measurements on the cat by interacting with them. Okay. So there's a whole bunch of measurements going on that we did not include in the original Schrodinger's cat paradox. Okay. So now, these gas molecules and these photons, these are different than things we usually think about in quantum mechanics, because the thing that makes an environment special is it's too complicated to keep track of the dynamics. Okay. For example, these gas molecules, there's probably an Avogadro's number of these things inside the box. I can't keep track of all of those particles. Okay, so inside the dynamics, I lose track of what's going on, and this environment leads to classical physics in large objects. Okay, and by classicality, I mean things like you don't have entanglement between objects, you don't have superpositions, the cat can't be dead or alive, or things like phase coherence. These things disappear via the interaction with these environments. And the reason we say things that have large mass are more classical is because in some sense, larger objects interact with the environment more often. Okay. Where an atom essentially doesn't interact with the environment at all. So this is why objects behave classically, but it also turns out that an environment can make quantum objects behave classically as well. So here I have a movie made by IBM. These are individual atoms that they're moving around. These are xenon atoms, right? And there is an environment in this picture, and it turns out to be this material that the atoms are embedded on. Those other atoms are always making measurements on these atoms here, and so the atoms can be manipulated like they were little balls. There's nothing quantum mechanical about these individual atoms. There's no tunneling, there's no superposition, there's no probabilities. I can move them exactly where I want and they don't go anywhere. And this is why you can make a movie. Okay, so the environment can make classical objects, or sorry, big objects, classical, and even small quantum mechanical objects can behave classically as well. So one way to get around this is we could say, well, let's remove all of the environmental effects from our system. Okay, for example, the cat. And it turns out this is impossible to do. You can get rid of the gas, you could probably try to get rid of most of the photons, okay, but there's always some environment, okay? And one of the questions today is gravity the ultimate environment? Okay, you can never remove gravity from a problem that has mass. Okay? And so people think gravity is really the ultimate environment. And so if we wanted to see quantum effects in a system that behaves normally as a classical object, we have to have a balance between two things. We have to have a balance between quantum dynamics and environmental effects. Okay, so we have to have a balance between the two to see at least some hint of this quantum dynamics. So if we want to see these effects in an object that has a large mass, then we have to do a couple things. First, we have to minimize the coupling to the environment. So in the real world, this means things like low temperatures or being in vacuum. Okay. We also would like quantum dynamics that are clearly distinguishable from classical motion. Okay, if the classical dynamics are the same as quantum, I can't tell what's going on. And we want a massive object, something that's fairly big, but we also want to have a simple theoretical model. Okay, so something very, very simple. And it turns out the best direction to go is to use a mechanical oscillator. So we're just going to use a standard harmonic oscillator. Okay? But we also have to add to this some kind of nonlinear interaction. The nonlinear interaction is required because if you try to work out the dynamics for a standard harmonic oscillator, the dynamics turn out to be the exact same in the classical and quantum regime. Okay. To see something interesting, you need a nonlinear interaction. And that's always true for oscillators. So one system that does this is what's called optomechanics. And optomechanics is a fairly simple device. So here I have two mirrors. These are these blue guys here. Okay. Inside of these two mirrors, light bounces around. The source of the light is this red arrow, which is a laser. And then one of these mirrors, this mirror on the left here, is attached to a spring. So it's free to vibrate. And so what happens is this light bouncing around interacts with this mechanical oscillator via the radiation pressure force of light. Okay. The radiation pressure force of light, you can actually see, it is the force that causes the tails on comets when you look up into the sky. Okay. So these are forced from individual photons. All right. And in this case, again, we need some kind of nonlinear interaction. And it turns out that you get a nonlinear interaction because when a photon enters this cavity, it pushes the mirror, but the next photon that comes in doesn't see the same situation. The mirror's been pushed back just a little. So there's some time delay in the dynamics, and this time delay can be written as a nonlinear interaction. I won't say anything more. So now there's two different regimes that are important in these devices, so I'm free to tune the laser's frequency to whatever I want. It doesn't matter. So there's two different regimes that one can have. So here I have a plot. This blue diagram is a Lorentzian that represents the density of states of my cavity mode. And here 0 would be if my laser detuning, which I'll call delta, is 0, which means I'm driving my laser on the frequency of the cavity. This is these points here. And then I can also detune my laser, which means I change the frequency of the laser. If I change the frequency such that it's now detuned by a frequency that's the mechanical oscillator frequency, omega m, then what happens is I shoot a laser at this frequency, right? But now my photons want to get inside the cavity. To get inside the cavity, they have to jump to this frequency over here. At this particular point, the extra energy these photons have is the exact same amount of energy as a quanta of the mechanical oscillator. So at this side here, at a higher frequency, it's called a blue detuned region. I send in a photon, it gives one excitation to my mechanical oscillator and then enters the cavity. And it pushes my mechanical oscillator. If I go on the opposite side, my laser, again, the photon wants to enter the cavity, but to do so, it has to take away an excitation from the mechanical element. So on this side, my mechanical thing gets more and more excitations, it gets hotter. On this side, I extract excitations from my mechanical oscillator and it gets cooled down. Okay? So those are the two regimes of interest in this particular device. And it turns out that the simple device actually has many uses in quantum optics and related fields, and it's explored in various different systems. Here's just a few. All right, so all of these can be described by the exact same physics I just told you. You have things like silicon nitride membranes. You have things like optical resonators, superconducting circuits. You have cold atom cavities, and the list goes on and on. Okay, I can't describe them all. The key thing is that if you look at the mass scales at which this simple model works, you go from grams and even higher to zeptograms. Okay? So there is a huge range of masses where this simple optomechanical system works. Okay? So we have the same physics over 20 orders of magnitude. Okay? This is a huge range of masses. So this is a completely general system that I'm talking about. And of course, because it works over such a wide range of masses, you can do lots of things. For example, you could do ground state cooling of a mechanical oscillator by using the red sideband and extracting excitations. You can look at quantum limits on continuous measurements, force, mass, position detection. non-classical states of light and matter, which is what we're going to discuss, entangled states, and so on. Okay. But even with all these different things, it turns out in general, this optomechanical interaction does not necessarily lead to non-classical mechanical states. Okay. And this is what I'm interested in generating. So what we need to do is, if we want to use the system, I have to find a related analog system that I know generates non-classical states and that I can map my optomechanical system on. Okay? And it turns out that there is such a system, and it's what's called a micromaser. If you don't know what a micromaser is, then you can think of this as a single atom laser. So please think of it like that. And so basically it is the interaction between a series of two-level atoms and a cavity mode. So here I've taken a picture from Serge Haroche's group in France. And so here what they're doing is these little circles are Rydberg atoms, and they pass Rydberg atoms through a superconducting cavity one at a time. Okay? So we only want the single atom in the cavity at a given time. The amount of time it's inside the cavity is what's called the interaction time. All right. So what happens is, if this superconducting cavity has a large quality factor, then by repeatedly passing atoms one at a time through this cavity, then you build up many, many interactions of this simple system, and this becomes a real quantum laser. You get quantum effects coming out of that. In particular, if you look at the steady state of this optical cavity here, the states are what are called sub-Poissonian states. And I'll explain that in just a second. But the main point is these are non-classical states of this cavity mode. Now the crucial parameter to understand the system is what's called the maser pump parameter. And it's just a numerical parameter that depends on how many atoms you pass through over the lifetime of the cavity, some coupling strength, and then this interaction time. The reason I'm telling you this is because if we vary this parameter, then what happens is the number of excitations in this cavity undergoes a series of transitions that look like phase transitions, and this is kind of the signature of a micromaser. And I want to show that I can reproduce this in this optomechanical system. So first let me briefly explain what a sub-Poissonian state is. So a sub-Poissonian state in physics is best characterized by what's called a Fano factor. Okay? Fano factor is a relatively simple idea. As you look at the number of particles in a quantum state, you look at the variance of the number of particles and divide it by the expectation value, and this is what the Fano factor is. So let's look at what the Fano factor is for two different states. Here is a coherent state, which is also called a classical state in some sense because it's the most classical state that one can have in quantum mechanics. And if you look at the distribution of the number of excitations here and probability on the y-axis, this distribution is a Poisson distribution. Okay. And in a Poisson distribution, the variance is equal to the average number. So if I calculated the Fano factor, I would get a value of 1. Okay. So the most classical states, I get F equals 1. We can go to the opposite regime and pick the most quantum of states that one could have in a harmonic oscillator. This is a Fock state. Okay, in this case, I picked n equals 3. And if you have a 100% probability of being in the n equals 3 state, well, then my variance is going to be 0. And my Fano factor, which is the variance divided by the average, is 0. Okay, so these are kind of the two limiting cases. So Poissonian has F equals 1. By definition, sub-Poissonian states are oscillator states with F less than 1. And the limiting case, of course, is a Fock state with F equals 0. One can go even further, and we can say that strongly sub-Poissonian states, so states that are close to Fock states, also have what's called a negative Bigner function. And the Bigner function is essentially the quantum analog of a phase space probability distribution. All right, so it's just measuring phase space distribution in x and p. but now X and P are not so simple to describe because now we have the canonical commutation relation between the position and momentum, and therefore this probability distribution doesn't satisfy all of the requirements of a real probability, so it's usually called a pseudo-probability. One of the consequences of this non-vanishing commutator is that this Bigner function actually can have regions where the distribution is negative, okay, which of course is impossible in a classical probability distribution. All right, and there's two, again, clear examples. Here is our coherent state that we just looked at. If I looked at it in terms of the Bigner function, what it would look like a Gaussian centered around a particular point. Here, x equals 3, p equals 0. It's a Gaussian and it's everywhere positive. Okay. So the most classical of states, everywhere the Bigner function is positive. Again, I can go to the Fock state, the most quantum state. I look at the Bigner function, and you'll see that it has regions that are negative. Those are highlighted in red. So the overall list of what's going on here is, if we start here on the classical side, we always have positive Bigner functions, and this Fano factor is always greater than or equal to 1. Okay. On the opposite end, we have negative Bigner functions, and f is going to be much, much less than 1. And somewhere in the middle, you can have a positive Bigner function, but f is less than 1. Okay. And this is the regime we really want to get to. These are the strongest quantum states. Now, if we looked at this like a probability distribution, this would not be very good because we have negative values, but it turns out, for what we're interested in, the negativity of this Bigner function can actually be used as a measure of how quantum your states are. Okay, so we can use this as a benchmark. All right, so now let's see how this all works out. So we're going back to our optomechanical system, the exact same picture I showed you earlier. And now I'm going to write down the Hamiltonian. Okay, the Hamiltonian has 4 pieces. First, I have my cavity, so the harmonic oscillator made by the light circulating in between the 2 mirrors. That's this term here. This delta is, again, this detuning value. Here I have the operators B dagger B. These are the operators associated with the mechanical motion of the mirror. All right, so those are the 2 oscillators. Here, this term here, proportional to E, this is my laser driving the x-coordinate of my cavity. So this is where my energy comes from. And then finally, the important term in green here, this is this radiation pressure interaction. So here I have A dagger A, so this is the number of photons inside my cavity, and B plus B dagger is the position operator for the mechanical degree of freedom. Okay. So if I put in 1 photon, this is 1, and then I would push my mechanical oscillator by an amount that's called G naught. This is the optomechanical coupling. Okay, you can also think about it now, if my oscillator has a non-zero x value, then because I have an A dagger A term, I also have one here. This term here shifts the resonant frequency of my cavity. Okay, so there's 2 different ways of thinking about this. So now we want to make this look like that micromaser or single atom laser that I just described to you. In the micromaser, it was the optical cavity that became nonlinear. I want nonlinear mechanical oscillator, so the mechanical oscillator will play the role of the optical cavity in the micromaser. And now I just need something that looks like a 2-level atom. Okay, but there's no atom in this device. So the key is you play a trick. So the trick you want to play is you have an atom that comes into the cavity and it emits a photon. And so I want to have something that looks like a single photon at all the time. So the goal is to consider this optical cavity as my effective atom by driving it with an extremely weak laser, so there's only a few photons in there, and I make the quality factor of this optical cavity very, very low. So most of the time, the photons come in and they get leaked into the environment. Okay. Only occasionally does a photon come in and interact with the mechanical oscillator. And if I do this right, then I can get a condition where the expectation value for the number of photons in this cavity is much, much less than 1, and this is a single excitation interaction. And the interaction does the exact same thing as the micromaser, even though we don't have an atom. So this is the regime I want to consider. Right. So first we have to look at the semi-classical dynamics before we look at the completely quantum version. And so in order to do this, you just write down Heisenberg equations of motion for my operators, and then you have to add the terms that are associated with the environment, which are 2 terms in this case. So these are just the usual Heisenberg equations of motion, also this term here. I have to add the terms for the environment, which in this case, this kappa term is the decay of energy in my optical cavity. So that describes energy being lost to the environment. And this term, big gamma m, is the loss of energy for the mechanical degree of freedom. So these 2 terms are my environment. So now, for the micromaser, all the interesting stuff that's non-classical happens in the steady state regime. So I'm interested in looking at the steady state. So I want to now describe the state of my cavity in the steady state regime. So steady state, I just set the time derivatives equal to 0, and I solve these couple of equations. And I get a 3rd order polynomial that describes the number of photons in the steady state for my cavity. Now the key idea here is that this equation describes a particular kind of nonlinearity in quantum optics, and this is called the Kerr nonlinearity. And in particular, the Kerr nonlinearity has a minus sign, and it goes as this coupling constant squared. So what happens now is if I plot the density of states of my cavity mode, if I did this, I would usually get this black Lorentzian here. But what this nonlinear term does is as I crank up this coupling, if I look at now the density of states of my cavity mode, it starts to be pulled to the left. So the frequency is starting to shift lower and lower. And this is what I've shown here. So the cavity frequency is in some sense being renormalized by this coupling, and we can now redefine the cavity resonance frequency to be the frequency at the peak of this bent Lorentzian. Okay. So as the coupling strength increases, the frequency gets lower and lower. Okay. I'll show you this again. So now we can also try to understand the dynamics of the mechanical degree of freedom by essentially taking a guess. So our guess is that the mechanical degree of freedom will behave like a normal harmonic oscillator. It'll have some static displacement we'll call x bar, and then it'll have some oscillations about that static displacement with an amplitude A. Okay, and now we want to go about solving for A and x bar, and you can do that. You can make a Fourier series solution, and you can actually obtain an exact answer. The answer is not so important, but you'll see that these alpha terms here, these alpha terms, if you take the absolute value squared, this is related to the time average response of my mechanical degree of freedom. And the important part is it's going to be peaked at values where this term in the denominator goes to 0. And this will give me a condition on my detuning at which the cavity has the highest response. And so you'll see that the cavity, the detuning value where the cavity has a lot of photons is given by some integer n times the mechanical frequency, here n times omega, where n is an integer, and then times a term that looks like g naught times x bar. And we'll see that this is, again, a nonlinear term. So at the end of the day, you have 2 equations to solve. You have to solve them numerically. So you have to self-consistently solve for x bar and A. Alpha contains both x bar and A, so you have to do this numerically, essentially root finding. But the key idea is that for a given set of parameters in general, there are multiple solutions for x bar and A. Okay, so you can have multiple solutions, multiple static displacements, and more importantly, multiple oscillation amplitudes. Okay, and in general, these are what are called limit cycles. So that is what we learned from doing